Good morning, students. Last class we introduced pure substance and water is the God gifted pure substance and how the stages of phase transformation is there. But our power generation, subcooled liquid to superheated steam is sufficient. So, how we are calculating the properties? Some of the properties we are extracting from the steam table, saturated liquid, saturation vapor. Superrated condition also, if round figures are there, 200, 250, 300, 400, like the temperature, superrated tables are there, we can, but subcooled we have to calculate. Or directly you can use the MOLLIER diagram, you can extract any state condition. Directly you can extract the enthalpy and entropy property by using the MOLLIER diagram. Today's class we will discuss about throttling process and some simple problems on especially on throttling. So what is throttling? Throttling, generally two applications are there. The representation of throttling process. First I will explain the throttling process. In refrigeration air conditioning, for achievement of desired temperatures in evaporator coil, what we are doing? We are throttling the refrigerator. We are reducing the pressure. While reducing the pressure, what we are maintaining? Enthalpy is constant. Throttling means iso-enthalpy process. Enthalpy is constant. What is the purpose there? To achieve the desired temperatures. And second application, generally industry application, refrigeration air conditioning separate, like a heat industry, wherever heat is required. Pulp and paper industry. The turbine exit, generally wet steam is there, maybe dryness fraction 0.8, 0.9. We want superheated steam. For that reason, what they are doing, they are reducing the pressure there also. Suppose at 1.01 bar pressure, saturation temperature is 100. If I reduce it to zero point 0.5 bar pressure, saturation temperature is 89 degrees. So at 1.01 bar pressure, if the steam have 100 degrees temperature, means it has some wet region condition. But I reduce the pressure without changing the heat value. If I am changing heat value, there is no use. Without changing heat value, enthalpy, I am reducing the pressure means that steam I will get the superheated steam. Transfer the superheated steam, it is easy compared to wet steam. Two phase condition to compared to single phase condition. So to increase the dryness fraction of the steam, we are using throttling process. This throttling is common for all heat utilization industry commonly. So what are the replications, conditions? One is pressure is dropped. Our target, we are reducing the pressure. If we are reducing pressure, volume is increasing. Entropy is increasing, there is no doubt. The representation you see, HS diagram, MOLLIER diagram. This is the saturation curve. Initial condition is there, the final condition. Enthalpy is constant, so I moved horizontally. But entropy is increasing. But enthalpy is constant. If you are assuming adiabatic process, there is no heat transfer and it is not producing any work. So work interaction also is zero. So how we are calculating the end steam is enthalpy is constant. Initial compulsory it is a wet steam. First we are marking in MOLLIER chart initial condition and at isoenthalpy means horizontally we are moving to the next pressure 1 bar to zero point 0.5 bar means we are moving to 0.5 bar pressure and we are marking the condition. It is below the saturation curve, it is wet region. Above the saturation curve, superheated region. And then you mark the points and determine the conditions. Condition of the steam. Two methods. By using general calculation steam tables, you can calculate the condition of the steam after throttling, or by using the direct MOLLIER diagram you can use. We'll solve some problem, then you will get the clear idea. Suppose this is one of the problem. A 1 kg of steam at 14 bar pressure and dryness fraction is 0.9. Throttle to 1.4 bar pressure. Determine the final condition. Simple. 14 bar pressure, dryness fraction and 14 bar pressure and dryness fraction is 0.9. Open the MOLLIER diagram. Where is the 14 bar pressure? This is the 14 bar pressure and 0.9 dryness fraction. Throttle to 1.4 bar pressure. Simply I am moving horizontally because this is a isoenthalpy. So this is not superheated region. This is also wet region around 0.95 something, 0.955. So it is also wet region only. Simply we can determine. Otherwise, write down the equation. Initial condition HF plus X into HFG. The final condition at 14 bar and at 1.4 bar HF plus X into HFG. Here you can determine the X value. You will get X value 0.956. From the diagram also almost we got a nearer value 0.95 above 955 something. So simple determination of the properties. End stage quality of the steam. Simple. Initial stage you mark in MOLLIER diagram 14 bar and zero point 0.9 dryness fraction and move horizontally because it is isoenthalpy process up to 1.4 bar. Second question also like that only. In throttling calorimeter, the pressure of the steam measured before and after throttling are 16 bar and 1 bar. Find the dryness fraction of steam before crossing the throttling calorimeter. So end condition they given 150 degrees superheated steam. End condition they given 150 degrees. So determine the H2 value at 1 bar pressure something 278.24. Next H1 value the X dryness fraction HF plus X into HFG. This X dryness fraction we want to determine. From the steam tables you can calculate the X value. Or second method I already mentioned while MOLLIER diagram. You see 150 degrees and 1 bar pressure. 150 degrees and 1 bar pressure we are moving up to 16 bar pressure. You see almost it is a nearer dryness only. That's why 0.99 near dryness, not 1, just less than 1 dryness fraction. From that point it is moved to superheated region, that 150 degrees. So throttling process you can do solve the problems in two methods, by directly using the MOLLIER diagram or by steam tables. Condition is enthalpy is constant, that's all. Next simple problems. 680 kgs of fish at 5 degrees are to be frozen and stored at minus 12 degrees. Fish they are stored, frozen and stored at minus 12 degrees. The specific heat of the fish above the freezing point, general condition is 3.182. Below the freezing point is 1.717 kilojoules per kg. The freezing point minus 2 degrees latent freezing point is minus 2, not 0. Generally water freezing point is 0, but this fish freezing point is minus 2 degrees and latent heat of fusion is 234.5 kilojoules. How much of the heat removed must be removed to cool the fish present stage, and what is the percentage of latent heat? That's all. Two questions. How much of heat is required and what is the percentage of the latent heat? Simple. First 12 degrees to minus 2 degrees sensible heat. Minus 2 to minus 2 degrees freezing point means solid to indirectly general liquid to solid condition. Minus 2 degrees. This is the latent heat. Minus 2 degrees to 5 degrees. This is the sensible heat. Mass is 680 into 3.182 specific heat, 5 minus 2 degrees means minus of minus 2 degrees, 7 degrees, plus the 234.5, this is the latent heat of fusion, into what is the mass 680 plus 680 into The specific heat is 1.75 to 12 minus 2 plus 12 degrees. Totally we will get 18,682 kilojoules. Out of that, what is the percentage of latent heat means? This is the latent heat. This latent heat by total energy. Automatically we will get the around 85 percentage is the latent heat. Simple. Two sensible heat and one latent heat. Same way, one more problem. Calculate the amount of heat required to convert 100 kg of ice at minus 10 degrees into steam at 100 degrees at normal pressure. Specific heat of the ice is 2100 joules per kg Kelvin, means 2.1 kilojoules per kg Kelvin. Latent heat of fusion also they given joules per kg. In kilojoules means 336 kilojoules per kg. Specific heat capacity of water is 4.2 kilojoules per kg, and latent heat of vaporization 2250 kilojoules per kg. They are all given in joules per kg. Same from minus 10 to minus 10 degrees sensible heat. The specific heat is 2.1. Minus 10 to minus 0 to minus 0 latent heat of fusion 336. Minus 0 to minus 100 water. Again the sensible heat 4.2 kilojoules per kg Kelvin. Next, minus 100 to saturated water to saturated steam. It is latent heat of fusion 200,250 into 100 kgs. Simple. So directly we can't calculate how many stages of phase transformation is there first. Right? That's why first class itself I introduced phase transformation from ice to steam. Each phase transformation, it is a sensible heat or it is a latent heat. That's all. That we want to identify. Sensible heat means MCP delta T. Latent heat already value they will give. Mass into latent heat. Summation of total heat interaction is the removal or addition will take place. That's all. Next class we will solve some problems on this properties of steam. Thank you. Thank you very much.